Hello everyone, welcome to Scholar Lab. Our simulations can transform your teaching approach, making lessons much more interactive and captivating for your students. Scholar Lab is a distinctive virtual laboratory that brings intricate STEM concepts to life through engaging simulations. This tool is crafted to aid students in comprehending and applying scientific principles in practical situations. Welcome to the world of thermodynamics. Get ready to dive into the fascinating process that governs the very fabric of energy and matter. This simulation isn't just about observing graphs and equations. It's about experiencing the dance of particles, pressure, and temperature like never before. Let's get started. Here we have two exciting parts, concept and playground. Under concept, we have isothermal, adiabatic, isochoric, and isobaric. Our journey begins with isothermal here, where the temperature stays constant. You can explore both reversible and irreversible processes. First, let's go with reversible process. Let's select our final volume by clicking on this drop down on your right hand side of your screen. What about 50? Now hit on the start button and watch the magic unfold. As the volume increases, the pressure decreases. It is creating a beautiful cascade of changes. Look at those graphs. Pressure versus volume, pressure versus temperature, temperature versus volume. They are not just lines, they are the story of how the universe maintains balance. Now, here's a challenge for you. You can ask your kids to solve this challenge. You can ask your kids to solve this isothermal reversible process to find out the work done, heat change, enthalpy, entropy, and ask them to give the correct answer by clicking on this question tab. Here you can enter the correct answer. Let me put 250 and clicking on submit. It will not allow to submit until you are filling all those answers for these tabs. You can check your answers by clicking on this bulb button, where that will give you the correct answer like this. Heat, internal energy, enthalpy, entropy, Gibbs free energy, and now you can click on submit to check the answers. You can click on this reroll button to do this experiment once again. Perfect. Let's flip it. Try out an irreversible process. Let's see how it changes. Now you can change the volume, final volume to, let's say, 40 and observe the changes. You can observe how the graph changes for reversible and irreversible changes. And don't forget to click on this question tab to reveal the answers for these parameters. Now we are stepping into the world where no heat escapes or enters. That is adiabatic world. Here we have two options, reversible and irreversible. Let's start with reversible. Here you can tweak the volume and calculate the final temperature by clicking on this bulb button. You can see the pressure and temperatures transform in real time. The graphs are back showing you the pressure versus volume, pressure versus temperature, and temperature versus volume. And just like before, test your knowledge with questions about work done, heat, and more. Let's dive into a reversible process too and feel the thrill of watching these variables play out. You can fill out the variables and click on Start to start the process. As a third part, here we have the pressure remains constant, that is isochoric process. Here you can enter the final temperature. Let me put 500 and hitting on Start button. As you can see, I have given the high temperature, the heat change happened over here, and the graph is plotted versus pressure versus volume, pressure versus temperature, and temperature versus volume. And the question button is your ticket to mastering the concept. Get ready to see how constant volume doesn't mean the constant excitement. Finally, here we are lock the volume in place and play with temperature. Set your final temperature and see how the pressure and volume react. Observe the graph shift and sway, capturing the essence of these changes. And don't forget to click on Question tab to reveal the answers for these parameters. And now, the most exciting part of our journey is playground. This is where the theory meets the real world application. And it's time for you to become an ultimate thermodynamic strategist. Here we have two types of playground, that is laws of thermodynamics and then Joule-Thomson effect. Let's start with laws of thermodynamics. First, let's set the difficulty level. How about 2? Get ready for the challenge. The challenge is to guide a man through this path to reach the highest work is done by the gas. Does it sound simple? Not quite. You need to select the correct parameters from the drop-down menu present in the right-hand side of your screen. Now you have to think carefully because each choice matters. After selecting these choices using the particular drop-down, you can click on Submit Final to reveal the answer. Red indicates the wrong answers. And yes, you will lose 100 points for each mistakes. And the clock is also ticking. We have only 25 minutes to crack this challenge. Want to try again? You can alter these parameters. Let me put closed and I'm removing the load. Heat to cool. Let's check how it goes. Great. So now the challenge works. Let's observe how the man moves. Now the step 2 is to move this man to the next level to T3 temperature. And for them, you have to alter these parameters again. Let me put remain same and let's check. Hooray, it's right. So the man should move now. Yes, the challenge is completed. There is always level 1 and level 3 waiting for you. Let's go to the second part, that is Joule-Thomson effect. Let's dive into this intriguing phenomenon. The Joule-Thomson effect states that the temperature of the gas can either increase or decrease depending on the pressure and temperature changes. Here we have two containers where the temperature is 27 and 22 respectively. And you can change the pressure of the container A by clicking on this piston. You can move your mouse cursor by click, hold and drag. I'm going to click on this piston to move this a bit. Now let's observe the temperature change and how the particles are moving from one container to another container. It is moving from high pressure region to low pressure region. But we are not just talking theory here. Let's see how this works in real life. Ready for something cool? Literally. Blow with your mouth wide open. Feels warm, right? Now purse your lips and blow again. Feel that refreshing chill? That's Joule-Thomson effect at work. But we are not done here. Let's take a tour on historical application. Let us take you through Jaipur to visit this palace. Can you see this Hawa model? How it works according to Joule-Thomson effect. Where the hot air enters through the wide opening of the window, these red waves are indicating the hot air. It is entering through the narrow openings and cool inside the mahal, where the blue lines indicating the cool chillness. It's quite amazing, right? But wait, there is more. Now we are going to the new age application of Joule-Thomson effect. Here we have different types of water bottles. You have to select a bottle to check and experience the maximum cooling efficiency through this water bottle. Let's select any of these. Let me select the first one. Now let's move on to select window tab. Here we have the house and where the hot air coming in from one way, and I have 3 windows in this house. One, the second one is nearby the door and the third one is left hand side. Now you can change the shape of the bottle going to be fixed on the window either inward or outward. Can you see the changes over here in this left hand side? Now it's time to fix this type of window to the house. By clicking on the window, it can be fixed as easy as that. Now it's time to check the cooling effect. I'm clicking on this check cooling effect to observe the change. The arrangement you have made has low cooling efficiency and the temperature difference is not reaching the maximum. You can try working on the other parameters like selecting the different bottles, selecting the inward outward parameters, and select the different windows. Thanks for watching.